go. Hey guys, so welcome to effectively Multicast 102. So this is a follow-up talk to the IGMP talk that I did previously. And so we're going to be talking about PIM specifically, and PIM, if you haven't seen that video, is the routing protocol that actually decides the path and forwards the multicast traffic. So there's a few modes and there's a few operational methods on how it can run, and what I'll do today is run through those two different modes and some of the messaging that happens at a normal protocol operation effectively. Now obviously I just mentioned IGMP there. If you haven't heard of IGMP, I do definitely recommend going and watching the IGMP specific video. That was Multicast 101, so definitely suggest going and watching that first. But I will touch on it very briefly, so if you've forgotten or if you just need a very quick refresher, that should give you that refresher. So you've probably seen this already, and I've given this slide before, but I think it's a good refresher on both of the talks. So with inside a network, you have three main types of data flows. There is a fourth, but you have three main types of data flows that most networks use and most people need to know about. So you have the standard, the Unicast communication, and that is that point-to-point communication from one source to a destination. That is you reaching out to a BBC web server, for example, and requesting the homepage of BBC. That is from you to then that server. Not directly, but effectively directly. It's between just two devices, direct per se, compared to the other two types of data flows. So then you have broadcast, and broadcast is usually used at a layer 2 domain, but it can be a broadcast message can be sent over a layer 3 network for a remote subnet. But that broadcast only acts inside a layer 2 domain or inside a subnet. And so what it does is it says it's effectively an all-host group. So the broadcast address is defined as like the last IP inside an IP subnet. So if you don't know what IP subnets are, I've done a whole video on L2, L3 addressing and data flows. Go and take a look at that before you even start thinking about multicast. But so broadcast uses that last IP in the subnet, and at a layer 2 layer, what it's going to do is it's going to flood out. When it leaves the router, it's going to have a destination MAC address of all hosts, or a broadcast MAC address, which is then going to end up in all of the hosts inside that layer 2 network. And so that's good if you want to send some kind of traffic specifically to all the devices inside a network. Now, anyway, there is then multicast, obviously the topic of this discussion, and that is point to multipoint usually. Now, you can have multipoint to multipoint, very much depends on your network, the use cases, but the generic use case is point to multipoint. So it's one source, let's say a video encoder, pushing out some kind of video streamer over IP to a network, so then you have multiple end hosts which might want to receive that traffic, view it, decode it, manipulate it in some way. And so you can imagine some kind of studio or some broadcast center where you've got some single source, let's say like a camera on the studio. That camera would be connected to a network and would be sending out a multicast stream. That then multicast stream could be pulled by many different destinations. It could be received by a display, a screen of some form, to just show out locally what is being recorded by that specific camera. Or it could be pulled by some kind of vision mixer or some kind of ingest server to, do whatever the production needs with that specific flow of data. So in essence, though, it has that kind of application where you can send from one device to a range of interested devices, and that's the concept of multicast. Now, multicast is also used for some control traffic. So you think about things like OSPF and other dynamic routing protocols and other networking protocols that control something. They inherently have to use multicast because they need to know, in the example of OSPF, who else is on the network, who else on the network is interested in OSPF or is an OSPF router. And so that's another use case of multicast outside of the media industry. Now there are a range of reserved addresses. Yet again, I touched on this before, and I think I mentioned it on a later slide, but there are a range of addresses, and those are specific for multicast. You can't use those standard IPv4 formatted addresses for your normal end hosts. They are very much specifically reserved for the use case of multicast, which is a lot of IP addresses, but obviously the specification and the reservation of multicast was a long time ago, where they maybe didn't realize the scale of the internet and things like that. So that's multicast in a nutshell. There's also then a concept called Anycast, and that's kind of similar to Unicast, but we intentionally duplicate IPs across a network to give you the ability to reach out to your closest IP. Yes, you're using duplicate IP addresses, but what you end up doing is you use your dynamic routing protocols to detect which of those duplicate IP addresses are the closest to your requesting host. And so Anycast is usually used for things like content delivery networks and those kind of things. So just to reiterate what Unicast looks like, what broadcast looks like, and what multicast looks like. In the case of sending some data from a source to a range of destinations. So in the case of this Unicast example, we have some kind of source here, and we have a range of destinations, both locally and remotely. So in this case, we've got 3 destinations and just one single source. This source, in the case of Unicast, is going to send out and have to generate 3 unique streams of the data that these destinations are interested in. That means the bandwidth and the links between the switches, this source to this switch, and the actual processing power on the source is utilized 3 times effectively, which obviously isn't great for the source and it isn't great for the network. You know, you look down then into the let's say the core of the network, this small network, and maybe there are bandwidth limitations here between these 2 routers. Well, in this situation, you're sending 2 times the amount of data across this link because you've got 2 destinations. Now imagine that studio example that I gave you, one camera outputting to a range of end devices. That could be in the range of tens, it could be 20, it could be a large amount of devices. You know, and it might not even just be it could be some kind of broadcasting source that has some kind of specific media. So that is Unicast. You know, it is well, it's good because it can get you from your source to your destination very specifically. It isn't so good in the case of, you know, the utilization of the resources that you have across the network. Take the example of this switch, for example. It has to manage and forward 3 times the amount of traffic than it would in maybe a case of Unicast. However, obviously in the case of Unicast, where you maybe don't have support for multicast in your network, it does mean that only the very specific destinations get the traffic, which is obviously a good thing in the sense of making sure that these end hosts don't get flooded with unintentional traffic. So that's Unicast. Now, looking forward to the other type of data flow that we mentioned, which is broadcast. So broadcast in this situation, you've got a source and it's trying to broadcast it across this layer 3 domain. In this situation, all of these end devices are going to receive that. Now, yes, only one copy of that traffic is sent from the source towards the switch, and the switch then forwards it on, and so on and so forth if you had a wide layer 2 network. But while that looks good, maybe only these 2 devices on the left-hand side are interested in that traffic. As a result, these 2 devices on the right are now going to receive flooded traffic for no reason, realistically. And let's take the example of a media or broadcast network. It's very notorious that some kind of audio devices or legacy devices, while they can deal with IP communication and traffic, if they receive the wrong traffic or they receive like a flood of traffic, well, that could send them over the edge and could potentially crash them. Now you've also got to think about, well, what is this traffic? Is that traffic going to be some kind of uncompressed, high bandwidth flow of some form? And if so, well, maybe these destinations can receive them properly. Maybe they're high performance multi-viewers or displays that are capable of dealing with that uncompressed data. Now, you've got to think, for the uninitiated that don't know media spaces too well, that kind of uncompressed data flow could be in the range of gigabits per second. Depending on the media and depending on the formats. So that being received by a device that might only have 100 meg interface, for example, would really cripple it. And so that's obviously where then other concepts like things like VLANs and breaking down your IP subnets can really help. But realistically, the best implementation would be multicast. And this is where then you build together those two concepts of unicast and broadcast together. So while it is flooded out across your network, it isn't flooded out to the devices that aren't interested. So let's say this is some kind of flow again, and we have some very specific interested devices here. And so you can see throughout the network only ever one stream or one flow of this originating data stream is being passed around the network. This means that these intermediate router links aren't going to be highly congested. These devices that aren't interested aren't going to receive the traffic because, well, they haven't requested it. They haven't joined the specific multicast group. These switches don't have to deal with too much traffic. These interswitch links aren't highly utilized, and specifically the source isn't then having to work overtime generating extra copies of the data. Now, the only thing to consider is the networking appliances in that network will then have to maybe work a little bit harder, because at each step they're having to potentially duplicate the traffic for the network, so these end devices actually receive it. So in the case of this router here, it's having to duplicate the traffic so that it can send it one out of this interface here towards this local LAN, and a second time down towards this other router for this other single host down at the bottom here. Now, depending on your devices, that will be fine, but obviously you've got to take that into consideration that, yeah, sure, multicast is great for these end hosts, but if your network is a bunch of older legacy devices, well, they might not support multicast. They might not have that support. They might be slightly buggy, but most importantly, they might not be able to handle this duplication. Now, I've never came across that, but it's something to take into consideration, certainly when you're dealing with maybe these larger flows of traffic. So that's those data flows in a very high level. But obviously, we're talking about multicast. So what do we need to make multicast work? What are those building blocks that I always talk about? Well, you've got the address ranges. So those are needed to make sure that those end devices know exactly what group they are registering to. There's no point just having some random assignment. It has to be very specific. Like your unicast traffic, you're sending your traffic to a specific end destination IP address. And so multicast has this similar concept. It has address ranges. As I've talked previously in the IGMP talk, you would have known about this. But then you need, obviously, a registration method. So one example of that is IGMP. Obviously, previous talk before this was around IGMP. So if you haven't watched that, go and take a look. But to keep it very short and simple, IGMP is the protocol that allows a specific end host to register or signal its interest in a specific multicast group. So if we just look back to this diagram here, if this end destination is very interested in this specific multicast traffic, what it's going to signal that it's interested to its local gateway or its default gateway, which hopefully should be running IGMP. Now, there is also an element of an extra protocol that can be run at these layer 2 switches, and that's what's called IGMP snooping. Now, I'll talk a little bit more in depth on the specific IGMP topic and talk, so if you are interested in that topic and you want to know a little bit more, go and take a look at that video. Otherwise, that's IGMP. It's controlling and it's managing that state of who is interested in what specific group. Now then we have the concept of today's talk, which is PIM, and that is a very common option for routing decisions. So while we know who's interested in the actual multicast group, we actually need to forward that traffic from that source network, maybe across a wider layer 3 network, to then an end destination network, an end destination host. So what PIM is doing is it's moving that multicast traffic, it's deciding the path for that source traffic from a host, from a source, across the layer 3 network to its end layer 3 subnet. Now it doesn't deal with end hosts specifically, rather it's dealing with which interfaces are interested in the traffic, which interface in what direction are there specific requesters for this multicast traffic. And so it doesn't track the specific end host status. That's why we have this registration method. Now, so as I mentioned, PIM is one of these well-known and common options for these routing decisions. There are other options. One of those examples is OSPF. There is an extension to OSPF that technically works for managing this multicast forwarding. However, it doesn't really scale that well, and I don't think I've ever really seen it in production. So your routing decisions mainly are going to be using PIM, and obviously within this talk we'll talk a little bit more about what that actually means. And then finally we have loop prevention. So I don't think I've touched on this too heavily in the other talks, but loop prevention is using what's called reverse path forwarding checks. But so very high level, loop prevention and reverse path forwarding is basically checking where you've received the traffic from, and then comparing it against your Unicast routing table to make sure that you've received it on the correct interface. Yet again, there is a specific slide on this later in the talk, so I'll go into that in a little bit more detail there. So as I mentioned, multicast ranges. There are a range of multicast addresses, and I believe I go into this in a lot more detail in the specific IGMP talk, but just as a really high-level view, they are broken off into specific use cases. So for example, this first range is a local layer 2 range, which is used mainly for control traffic between different devices, but is only specifically used for local layer 2 domains. So you can't span that out over different layer 3 domains. Now there is also then different ranges for different things, right? So this is only just a few examples of ranges. Now one or two that are very specific is this source specific multicast group, and that allows us to effectively specify a source IP address that is linked to the multicast address or group that we are interested in. Now that allows us to specify a specific source address of traffic where we are expecting multicast to be sourced from. So if I just run us back to this, so here you have two different sources, let's say, and so maybe one of these is a encoder that is encoding completely uncompressed data. I say encoding, but it's encoding, let's say, from a raw camera into an uncompressed IP flow across the network. Now that's great for raw data storage, transmission, whatever you want to say. But maybe this other one is a lower bitrate one where you can just pop it onto a screen and not have to worry too much about the exact quality, but just have an idea of what the picture is, for example. And so that could be imagined like, how on YouTube you select, I want 4K or 1080p or 720, for example. And you could have different sources of multicast, so that the actual content, the actual video that you're seeing on the multicast is of the same content, so it's coming from the same camera, let's say, but maybe there's different data rates of it. And now there's obviously different ways that you can actually achieve that. But one of the ways that you could achieve it is by having source-specific multicast, and then allowing you to specify the IP address of that specific source that you're interested in. So that's source-specific, and the only other one that I'm going to very quickly dig into is the locally significant one. So there is a range that allows you inside your local company or inside your local network to use a range of multicast addresses, a very big range realistically, but those should not be scoped outside of your company or outside of your local network, or specifically your autonomous system, right? So while these two specific ranges allow you to scope multicast across, potentially across the internet or across a wider range of networks, this final one down here is locally significant, and it should be blocked when you're trying to forward out of your local network. So, PIM, how does that actually look? Well, PIM has a range of fundamental building blocks, very much like multicast operation. You've got a protocol mode, so that could be sparse or it could be dense. Now, there's two different modes there. So, sparse is effectively allowing you to, as a end destination router who has interested or registered hosts behind it, to say, yes, I want the traffic, give me the traffic. And so in that sense, it's more complex. It's more complex to implement, and but it's a bit easier to manage from an operational standpoint. It also means that you're saving bandwidth and you're saving CPU compared to dense mode. And so dense mode is very easy to configure, because the concept of dense mode is that it will just forward out traffic, and those end destinations or those intermediate routers will say, hey, no one's interested, stop sending the traffic. But anyway, we will get on to what that actually means in a later slide. We then have a concept of a rendezvous point, and now that's specifically used in sparse mode to identify like a central point in the network where any destination router can go towards that rendezvous point, and it can say, hey, I want some multicast, can you send it me? At the same time, source devices will be sending their multicast traffic in that kind of direction to register it onto the network. And so you can imagine this rendezvous point as some kind of central control device which stores some state within inside it. So we can reference that at a later date when someone is interested, and we can say, hey, yep, I know where this multicast is, I'm getting it so I can forward it on to you if I want. And that's why we have this rendezvous point. Yet again, I'll get into why that's really important in a later slide. Now we have then a designated router, and yet again, that's used in sparse mode specifically to say which router is sourcing the traffic. And so that's really important to know, because then you need to reference it in other parts of sparse mode. And then you have reverse path forwarding, and as I mentioned, that is all about making sure that you are receiving traffic on a very specific interface that is the correct interface where you would have forwarded traffic towards for the specific source of the multicast traffic. Yet again, I'll dig into that in a little bit more detail, because that probably doesn't make sense right now. As I just mentioned, reverse path filtering is basically locally double checking that the multicast traffic that you've just received in your interface is the correct interface to receive it on. So in this example, what we're doing is we've got some kind of source up here that is sending traffic out onto the wider network, and we've got a destination here. Now this multicast traffic is being flooded across all networks, and we're receiving it across all of these three interfaces. Don't ask me why this would be a valid network, but I think it's a good example. Now, for the time being, ignore these red stops, but you can imagine that after reverse path filtering, this is where we would stop. Anyway, how do we understand, how do we know that that is the case? Well, this router here is going to receive this multicast traffic in three directions from three different interfaces. As a result, it should know about state via all of those relevant interfaces to a certain degree. Now, on its routing table, maybe this is incorrect technically, but if you were to show all of your routing information before you disregarded the worst routes, what you would see is potentially different metrics for these different interfaces. And now, for some reason, G01 has a cost of 50. Interface 2 has a cost of 100, but then interface 3 has a cost of 10 towards this end destination IP address, or in this case, the source of the multicast. And what this device can say is when it receives this traffic, it knows that it was sourced from this 1.1 address. And yet again, when it receives it on interface 2 and interface 3, it knows that it came from this interface. But because it's got 3 copies of it, it needs to know, well, wait a sec, which one is the correct interface that I should have received it on? Now I look in my routing table and I see, okay, the best path towards the source of this traffic is via interface 3. So okay, well that must be the shortest path. So I'm going to accept it here, and I'm going to block the traffic coming from the other interfaces and drop it. Now that state doesn't get passed up towards these routers. This reverse path filtering checks are effectively local to the routers, but there is an element of this which then plays into the PIM operation, which can control this to a certain degree. So that's reverse path filtering. It's a little bit of a complex concept, but once you just see it in a very simplistic sense, hopefully it makes a little bit more sense. Now, as I keep on badgering on about PIM and this dense and sparse mode, let's talk about it a little bit more. So, in the dense operation, and before I get going, I should note I have got some further slides after this which will detail the operation of these 2 different modes. So if you don't want just to hear the details and you want to actually see the actual example, skip ahead a little bit and you'll see that detail. So we have dense mode. That will initially flood that multicast that it's receiving into the network, and then those end devices will explicitly prune the traffic and say, hey, no one's interested connected to me, stop sending me this multicast traffic. So in that sense, the sending router is effectively hands-off and it doesn't care, but then these destination routers need to be able to say, receive it, and then process it and say, actually, no one's interested. Really, stop sending me this traffic, it's a waste of time. Now, dense mode is very simple. It's very simple to set up, but obviously it uses more bandwidth. The way that dense mode works, and to make sure that everyone has the understanding of the network, is that it will send out the traffic, it will flood the traffic. After a while, these end devices will then specifically prune the traffic, and you'll dip down with the bandwidth utilization. But after a period of time, once the counter is expired, I think it's around 4 minutes or so, dense mode will then kick into play again, and then it will flood the traffic once more across the network. As a result, you get spiky bandwidth utilization, and potentially you get discarding randomly at transient intervals, effectively, and as a result, you will be scratching your head thinking, why am I getting random bursts of traffic? Because obviously, routers aren't slow to act and send control messages. This will be a matter of a second or 2 spikes of traffic, which would then get flooded and then pruned again once those destination routers have understood that. So really, dense mode isn't really useful unless you have got a dense spread of specific multicast receivers. In that situation, that would be perfectly fine, because you're sending it to all destinations across the PIM domain, and if all of those destination devices are with receivers that would be interested in that multicast traffic, well then that's fine. We would set up the tree, we would send the traffic, and no one would be complaining. But if you've got, let's say, one receiver in a very wide PIM domain, well, you're sending this traffic around the network for no use, which is causing potentially discards, potential more utilization in the bandwidth, And it's also increasing the CPU on these devices, because they have to receive the traffic, process it, and understand what's going on, and then forward back towards that originating device and say, hey, stop sending traffic. That in itself takes up some CPU time on the router, which obviously isn't optimal. Now, one good thing with dense mode is that it uses what's called source-based trees, and I'll get on to what I mean by trees later. But what this means is we are sending traffic automatically, straight away, via the best path, the shortest path, because we're sending directly from the source and then flooding across the network. As a result, you're automatically getting the best path. That's how flooding will work. And linked in with the RPF checks, you would only an intermediate device would only receive that traffic on the best path interface. So as a result, you would only follow the best path across the network. Now, you then have sparse mode in contrast. Well, that only sends that multicast on request. Now, the exception to that is when that designated router, that originating router, sends the traffic towards the central rendezvous point. So remember, I mentioned with those building blocks, with inside sparse mode, we have a thing called a rendezvous point. And that's a central place where we want to send all multicast traffic to, so that that rendezvous point can register it and make sure that everyone understands where that multicast is from, and that they can receive that multicast by just going towards the RP. Now, of course, with inside your network, you need a little bit more of a complex configuration. So the RP needs to be defined or elected, and then around the network, you need to make sure that those destination and source routers know about the RP and know explicitly what device is going to run as the RP. Now, that RP can't just be some poxy device that you just got off the shelf that's been sat there for 10 years. It needs to be a device that can manage all of this state and can also process all of this multicast traffic, while potentially only on a small time basis, but it still needs to be able to receive it and process that. So you can't just use any poxy device on the side of the network. It really does need to be something relatively in the core of the network to actually work properly. Now, with the case of sparse mode, it has a little bit more complicated source discovery. A destination router or a receiving router would signal towards the RP first before it signals towards that originating router. Now, it's obvious and very important to note that there is a source-specific mode of sparse mode, which then goes very much directly towards that source destination address, which should obviously lead towards that designated router, the originating router within inside that PIM domain. Now, so sparse mode uses what's called shared trees. So those are more bandwidth efficient, at least in the short run. And so what that means is we're sharing a path between that source router, that originating router, and then the destination. So that shared tree, or that shared path, is usually going by the RP, the rendezvous point. As a result, we're sending one copy of that traffic across that path towards the rendezvous point, regardless of how many people, destinations, are interested. Now, once a destination router is actually receiving that multicast traffic, it can set up a source-based tree or source-based path back to the originating router if it thinks that the current path is inefficient and not the best path. So yet again, I'll touch on examples with all of this in some later slides, but it's really important to understand that dense mode is good if you have a wide spread of receivers for specific multicast groups. And sparse mode is really good if you have a wide, large network with a sparse scattering of devices that are interested in that specific multicast traffic. So, with inside dense mode, we have a range of messages. So we have a hello message. Now that is used to establish neighborships and adjacencies. That allows us to identify specific settings that need to be agreed on between neighbor devices. And so, if I haven't mentioned it already, PIM is one of those routing protocols dynamic protocols that require these adjacencies between devices that are running PIM, so that we can send our specific state between those devices. Now we also have what's called a prune message. So as I mentioned before, this is used when you want to stop receiving traffic. And the way that that works is that it's sent upstream towards your neighboring router in the direction of the specific source that you're receiving multicast traffic from. Yet again, we'll go over specific examples of all of this in a later slide. We then also have a graphed and a graphed act message, and so that allows us, between those flooding intervals with inside dense mode, it allows us to join back onto a multicast stream explicitly and say, hey, yeah, we're really interested in this, send us the traffic again. We then have the acknowledgement message of that to actually confirm that the upstream devices have received that graphed message. Now we also have an assert message, and that's a little bit more theoretical to a certain degree, and that is used for those multi-access segments to actually identify which device should be a designated router. Very much similar to what is called a designated router with inside OSPF. You know, if you have a multi-access segment, then you can set up a specific designated router so that only that router will send traffic in those specific use cases. So, getting into the actual operation of dense mode, what does it look like? Well, when we have this multicast source come on, what it's going to do is it's going to send that multicast traffic to its local default gateway effectively. That is then going to be flooded across the network to a range of devices. And so let's say in this case we have a requester down here, then we have 3 different devices over here. What's going to happen is these devices are going to carry out those normal RPF checks to make sure that, you know, we pass that check and make sure that we are receiving traffic in the right direction. And then what is going to happen is these routers on these end devices here are going to check their state, and they're going to say, is anyone actually interested? And now this is where IGMP comes into play, because we compare state we pull in state effectively from the IGMP table to say, is anyone actually interested in this group? Is there any requesters or any specific interested parties for this specific multicast? And if not, well, what the router will do is it will send a prune message back upstream. So in this situation, we've got these 2 devices to the right hand side which aren't interested and don't have any requesters beneath them. They're both going to send a prune message upstream towards their PIM neighbors. Now let's imagine in this situation, one of these devices, let's say the left hand most device, is actually interested in the traffic. This right hand device, this right hand router, destination router, is still going to send its prune because its connected devices aren't interested. But this intermediate device will actually see, okay, hold on a sec, I have an outgoing interface towards this left hand receiving router. Well, let me not hold off sending traffic there till I receive a prune. And let's say in this case, actually that prune message is just a little bit delayed. Well, in that situation, this intermediate router will actually say, okay, no one now is interested, let me send a prune message upstream towards my neighbor. Now, this device sees that it has some kind of requester behind another interface, and it doesn't send a prune upstream. What happens is upstream still sends that multicast traffic, but this intermediate device in the middle stops sending that multicast traffic out of its local interface to the right-hand side. And so what these devices actually do in the background, they start storing state for these specific groups, what's called S, G states. And so that S stands for the source, and the comma and G stands for the group. So we match up a specific source to a specific group. And we then store these incoming interfaces and those outcoming interfaces. So we have, in this situation we have some kind of incoming interface of A, and then we have outgoing interfaces of B and C. So we know that there are people or devices specifically interested out of these specific interfaces. And that's how these routers store state. They map a source to a group, or at least a group, to then incoming and outgoing interfaces, so then they know locally what their state is for that specific group. If no interface is in this outgoing interface list, well then that device knows that it can send a prune message upstream to say, hey, I'm no longer interested in this group, stop sending me traffic. And so that's very much how this dense mode operation will work. It'll flood traffic. These devices will check and store their s,g state, but they'll see that there's no interfaces in those outgoing interface lists, and as a result they're going to prune that traffic away and remove that state, because there's no need for it. Then obviously every 3 minutes, as I've mentioned here, but I imagine each vendor has their own implementation, but after every 3 minutes we're then going to flood the traffic again, get that new state, and then that whole process is going to keep on looping. Now obviously if one of these requesting devices or end receiving routers is interested in traffic after they've pruned that message, well, they need to have some kind of method in which those end devices can actually receive the traffic. And so this is where that graphed message comes into play. So what these end devices will do is they will graft upstream towards their neighbors. And that'll usually be triggered by some kind of IGMP state change. So usually some kind of report or join message from their local network saying, hey, I'm now interested in this Multicast group, please send me this traffic. As a result, your neighboring or upstream devices will then process that, look in their state tables and say, do I need to request this state again? Yes. Okay, I'm going to send another join, another graphed message upstream, and eventually it'll the network will then start forwarding that multicast traffic once you've actually formed that multicast tree again. So that's dense mode in a bit of a nutshell. Hopefully that made sense. If it didn't, let me know in the comments and I'll try and explain a little bit further. So we then have Sparse Mode. So Sparse Mode has their own set of specific messages. So things like the hello messages are very standard across PIM. But we then have what are called join messages and prune messages. So obviously we heard about the prune messages. But because the way that Sparse Mode works, we explicitly show interest in a specific group. So what we need there is this specific join message to say, hey, yep, send me the traffic, someone is interested in it. Now that's regardless of whether there is actually that multicast group on the network, but what that router is doing is it's saying, hey, if someone's interested, try and send me the multicast traffic. That goes towards that rendezvous point, and then the rendezvous point evaluates its state and then potentially forwards on the traffic. Now what we also have is those assert messages, again very much similar to how they operate with inside dense mode. We then have register and register stop messages. Now these are very specific to that rendezvous point or RP operation. So what a designated router, or the router, the originating router that has the source behind them, does is that when it receives that multicast traffic, it's going to encapsulate an initial multicast packet with inside a register message. And that register message goes directly to the RP to say, hey, have this multicast traffic, please send it on towards me, so then I can then process it. So the designated router encapsulates and then sends that multicast traffic encapsulated with inside a register message towards the RP. Once that's received, the RP then obviously knows the state. It can decapsulate the register message. It knows then the traffic underneath is the traffic that we're trying to register. So as a result, we can see the source address and we can see the multicast group that we're interested in. And so we can form that s,g state on the RP. As a result, once that is received, any requesting devices now can actually get the traffic. The RP is then going to join upstream towards that designated router and say, hey, I have interested devices behind me, send me the traffic. That designated router is then going to forward it on, and those end devices are then going to have that state. Now there is then also bootstrap and candidate RP advertisements, and they are effectively facilitating the election of a dynamic rendezvous point. So with inside PIM there are two methods in which we can elect and define RPs. One is static and one is dynamic. And within inside the dynamic range we have then candidate messages to say, hey, I'm a candidate, I want to be eligible for the RP election. And then we have bootstrap messages. And those advertise the specific result of the RP elections. So, moving on, how does this actually look in a network diagram? We're almost there, we're almost finished. So, we have some kind of source. It sends this multicast traffic towards this specific destination group. This is then stored on this designated router as what is called that S,G state, because we know the specific source and we know the group that we're trying to send traffic towards. So that gives us that ultimate state locally. This router, because it's within inside this wider PIM domain, so we can assume all of these devices are in the PIM domain, it's going to encapsulate the first packet of this multicast traffic in a register message, and it's going to send it directly towards the rendezvous point, in this case this device here. As a result, that rendezvous point is going to register that traffic, and it will store it within inside its multicast state table, whatever you want to call that. That's going to yet again have that source and group or S,G state. So, happy days. We've got the multicast in the network, but now, well, we have a requester. So this requester is sending an IGMP report message saying, hey, actually I'm really interested in this traffic, send it me. So IGMP process on the local routing device is then going to pass that state up towards PIM in some sense, and then PIM is going to say, okay, great, I have this star,G state. So instead of having an S,G state, we have a star,G state, because all the requester knows is, hey, I want to get this group, this multicast group of traffic. And so, if you remember before, I was mentioning about source-specific multicast, or sparse PIM. Well, what will happen in this case, sparse PIM, is we will actually, source-specific PIM, is that we will actually have this source state on this destination device, and instead of going towards the RP, we're going to go directly to the designated router or the originating router. But that's not the case today. This is just standard PIM sparse mode. So the requester just has this normal star,G state. It doesn't know the source. And that's all the router has. So what it's going to say is, okay, I don't know the source, so I'm going to go towards the rendezvous point. The rendezvous point should have this multicast traffic, and if it doesn't, well, I can register my interest there. And when there is multicast traffic, I can then receive that multicast traffic. The rendezvous point knows I'm interested, so it then start forwarding at me. So what we do is we look at our routing table and we say, what's the RP? Okay, it's out of that specific interface. We start sending PIM join messages upstream towards the RP. Now this doesn't go directly to the RP. This goes in hops. And the reason why we have these hops rather than going directly is because any intermediate devices need to know that they have an outgoing interface now for this state. So while we have this star,G state on this 1.3 device, we know obviously we've got an outgoing interface that is connected to this requester, and we have some kind of incoming interface potentially that could potentially be identified. Now this .2 router here in the middle, when that receives the PIM join message, it's going to say, okay, I've just received a join. Someone outside of that interface is interested in this specific star,G state. So it itself is going to store this star,G state. It's going to identify, okay, I've got an outgoing interface that is registered and that is interested out of this interface. As a result, I need to then request this multicast state because I don't know it. So I'm going to send a join upstream towards the rendezvous point. At this point, the rendezvous point knows, okay, I have this S,G state, and someone's joining this. So right now, this rendezvous point just has that standard source and group state, but it doesn't have any outgoing interfaces. It knows where it can receive the traffic, so it has an incoming interface. That's wherever it received the PIM register message from. But its outgoing state, it has nothing right now. Now, because it's just received a PIM join message, it can update that outgoing interface and outgoing interface list. And as a result, that RP is going to say, now I have requesters. Now I have people who are interested in this traffic. So in the next slide, what we see is this rendezvous point is actually then going to start sending a PIM join message upstream again, which is fantastic. It's going to start requesting traffic, very much similar to how we did it before, hop by hop. So this intermediate device is going to know, okay, I have an outgoing interface here. So if I have this traffic, if I receive this traffic, I'm going to send it out of that incoming interface and that outgoing interface. And then we yet again send a PIM join message towards this .4 address, this .4 device, which is the designated router, to say, hey, actually, now you have an outgoing interface. You have an incoming interface before, and now you have an outgoing interface for this group. So let's start forwarding traffic. At the same time, this rendezvous point is going to say, hey, stop registering. I know it now. I know the multicast. I don't need to see your registration messages. Now, technically, this happens a little bit earlier, once we received that original register message. So, slightly incorrect diagram here, but hopefully that makes sense. We would send that register stop message to say, hey, no longer interested in the register messages because I've stored your state. I've received it. So, once we've received these joins along this top path here, well, everyone now knows all of the state. It knows the outgoing interfaces, and it will soon know the incoming interfaces. At least it knows that *G state along the path. And so, because we've had these PIM join messages, what we're doing is effectively setting up the forwarding path that we will follow for this multicast traffic. So in this following slide, what we can say is we have this multicast traffic going out in the direction that we've just received those PIM join messages in. So it goes all the way towards that rendezvous point and then back down towards this destination device. Now what's going to happen is this destination device is going to receive that multicast traffic, and it's going to process it, and it's going to say, okay, interesting. The source is this specific address. Well, I'm going to RPF check that, and I'm going to say, well, that's not actually the best path. We can assume that, let's say metric of 1 on each of these interfaces. Well, we've got a metric of 4 to receive this traffic right now. Actually, I have a better path of just a metric of 1, going direct towards this designated router. So why am I going via the RP? I have no idea, because I have a better path. So this receiving router is frustrated, and what it's going to do, it's going to say, I don't care about this path. I want to set up something direct. So because it now knows the source of that group, it can send a join message that is a lot more tailored to this specific device, and a lot more tailored to the specific location that it is inside this network. So in this situation, we're going to just send a join message directly up towards that designated router, that originating router. Once that originating router sees that join message, it then starts forwarding that traffic out of another outgoing interface that it has inside its list. So this designated router at this point has 2 interfaces, one pointing in the direction of the RP, and then another in the direction of this destination device. As a result, this destination device now has 2 lots of multicast traffic being received. It has 2 potentially incoming interface lists, so obviously that's not intentional, it's inefficient. So what it's going to do is it's going to send that prune message upstream towards the RP, where it was previously receiving that state from. Yet again, that prune message is going to go hop by hop, and that is, yet again, specifically to make sure that no one else behind this intermediate device and all the intermediate devices along the path have any other receivers that are interested in this multicast group, any other outgoing interfaces in that outgoing interface list. If we don't, when we receive this prune messages, we're going to process them, say, okay, I don't have anyone else interested behind me. So I am going to prune upstream towards the source. That then hits the RP. The RP does exactly the same process. Is anyone interested still? Do I have any other outgoing interfaces in my outgoing interface list? Well, no. So I don't need to receive the traffic. So I'm going to prune, yet again, all the way back towards the source. And as a result, right at the end state, once everything is set up, it's very much a very simple path for that multicast traffic to flow over. You know, it's one hop of multicast traffic towards this destination. So that is the final state. Very simple. Multicast traffic goes from, you know, your designated router. It has its outgoing interface list, which just has one interface. And as a result, that destination router is then going to receive it, and it's going to be able to forward it out onto its local subnet where its receiver sits. Obviously, with this being the end state for this specific exchange, there are still things going on in the background. You've still got PIM hellos exchanged between all of these different PIM neighbors to make sure that they all retain that state. They all know that, you know, this device is connected to me locally. Now, sadly, in the way that PIM works, we don't have this state of this multicast traffic locally stored in any other device than the originating device, the destination device, and this rendezvous point. So a good example of why that is a bad thing is, you know, if this intermediate device now has a requester, well, it's got to go through that same process again. It's got to go to the RP, say, hey, I'm interested. The RP has then got to join towards this designated router. Designated router forwards via the RP back down to this interested router. And yet again, the requested router is going to say, hey, that's a bad path. That's a metric of 3 rather than a metric of 2. It's going to join towards this device, which already has the multicast state, so it doesn't need to do anything other than update its outgoing interface. It's then going to prune all of this and so on and so forth. So a slight disadvantage to sparse mode there, but obviously more efficient than things like dense mode. Now you can make that a lot more efficient by using what I mentioned earlier with the specific source specific sparse mode operation. So if there's a requester behind here that knows the specific source, this router here then now knows, okay, we've got an S, G state. We've got that ultimate state which says where the multicast traffic is originating from. We can look up in our table and then we can go very much directly to this designated router, this originating router of the multicast traffic. So that is sparse mode, and that's PIM as a technical introduction.